Hello and welcome to this video. Here we're going to take a look at an application of systems of linear equations. And our goal here will be to do a couple of things. One, to build the appropriate models being the two linear equations that we're dealing with, and then to employ a solution technique. And we're going to focus here on using the method of elimination, because the method of elimination actually leads to a really convenient algorithmic approach to making further problems much faster to solve, regardless of how many variables they have. So when we begin taking a look at a problem, let's read it first. Acme Baby Foods mixes 2 strengths of apple juice. 1 quart of beginner's juice is made from 30 fluid ounces of water and 2 fluid ounces of apple juice concentrate. Okay, so we know we have this beginner's juice, and it has some water in it, and it has some apple juice concentrate. 1 quart of advanced juice is made from 20 fluid ounces of water and 12 fluid ounces of concentrate. So now we have the second potion here, and these add up to a quart, 32 ounces. That's 1/4 of a gallon. So we have 20 fluid ounces of water and some more apple juice concentrate here. Every day, Acme has available 30,000 fluid ounces of water and 3,600 fluid ounces of concentrate. Okay, so we have limitations. We can't just do whatever we want because we're limited in our resources. If the company wants to use all the water and concentrate, how many quarts of each type of juice should it mix? Well, the question itself is what determines what our variables are. So what is unknown in this problem? Well, we want to know how many quarts of each type of juice should it mix. So our primary question here is how many quarts of each type of juice should it mix? And that's unknown, right? At this point, we could say that we want X quarts of beginner's juice and we want Y quarts of advanced juice. Of course, instead of using X and Y, maybe we use B and A for it. And that's totally a matter of preference. In fact, let's go ahead and just stick with X and Y since we only have 2 variables. So what is X a variable for? What is it a placeholder for? Well, it's the number of quarts of beginner's juice to mix up. Right, so this is going to represent how many quarts of that beginner's juice we're going to be able to mix up, given that we have 30,000 fluid ounces of water and 3,600 fluid ounces of concentrate. And then our second variable, Y, will be the same thing. Just put, same thing, but this will be for the advanced juice to mix up. And what's going to keep us from arbitrarily picking, I'm going to make 40 quarts of beginner's juice and 100 quarts of advanced juice. Well, we have limitations. We have one limitation here, 30,000 fluid ounces of water, and we have 3,600 fluid ounces of concentrate. And we know that every quart of beginner's juice is going to use up both water and concentrate, as is advanced juice. So I'm going to write what are my constraints. What are the real world constraints? So we want to use 30,000 fluid ounces of water. We want to use it all up. We could use less, we just can't use more. So if we're going to be able to sell all this, then we want to use up what we have available and use up 3,600 fluid ounces of concentrate. Now, you could hypothetically start plugging in numbers for X and Y and saying, well, how many fluid ounces of water would, say, 10 quarts of beginner's juice and 40 quarts of advanced juice use up, and then would that still allow us to have enough concentrate available to do it. And that's obviously going to be a very futile way of doing it, because eventually our guess and check method is going to run out on us. It's not going to be very useful. Okay, so let's think about this. So every quart of beginner's juice is made up of 30 fluid ounces of water and 2 fluid ounces of apple juice concentrate. So if I were to have, say, 1 quart of the beginner's juice, then that would require 30 fluid ounces of water. And if I had 1 quart of advanced juice, that would require 20 fluid ounces of water. Now, that's just for the water requirement. The water is going to come from a combination of how much beginner's juice and how much advanced juice we make. If we had 2 quarts of beginner's juice, then we would need 60 fluid ounces of water. And if we had 2 quarts of the advanced juice, we would need 40 fluid ounces of water. So this is the amount of water we need. And already we can see that the amount of water we need is going to be a multiple of the number of quarts we produce. In fact, we could say that if we have X quarts of beginner's juice, then we're going to need 30 times X ounces of water, since for every 1 quart we require 30 fluid ounces of water for beginner's juice. And similarly, if we had Y quarts of the advanced juice, then we would need 20 times Y ounces of fluid ounces of water. Together, if we add these up, if we have 30X ounces of water plus 20 Y ounces of water, that has to equal how much water we want to use up, which is the 30,000 fluid ounces. So you can see that if we do a dimensional analysis here, a unit analysis, 30 is the number of fluid ounces per quart of the beginner's juice, and multiplied by X, which has units of quarts of beginner's juice, then we see that those units cancel out, and that product right there gives us the total number of fluid ounces of water. And similarly here we have the same thing. Fluid ounces per quart of advanced juice times the number of quarts of advanced juice gives us the total fluid ounces of water. Fluid ounces of water plus fluid ounces of water equals fluid ounces of water. In a similar argument that we could make here, if we have 1 quart of advanced juice, we're going to need 2 fluid ounces of concentrate. And similarly, for 1 quart of advanced juice, we're going to need 12 fluid ounces of the concentrate. So if we were to have, say, 3 quarts of beginner's juice, that would require, well, 2 for each quart. So 2 times 3 is 6 fluid ounces of concentrate to make the 3 quarts of beginner's juice. And if we had, say, 5 quarts here, they don't have to be the same, then for each quart we would need 12 fluid ounces of concentrate. So 12 times 5 would give us 60 fluid ounces of concentrate. And in the same line of thinking that we had here, if we drop down to saying, well, what if we had X quarts? Well, we need 2 fluid ounces for every quart, so 2 times X fluid ounces of concentrate would be required, and over here, 12 times Y would be required to produce Y quarts of the advanced juice. Summing those together, the fluid ounces of concentrate plus fluid ounces of concentrate has to equal how much we want to use up, which is the 3,600. Great. Well, now that we have our system of equations built based upon the constraint, we define the variables, it's important to take this time to do it because any mistakes can be caught now before we start doing the mathematics on it. Now our focus is to figure out what is x and what is y, and we have multiple techniques with which to do it, but as I mentioned, we're going to want to do this with elimination because this will lead to an algorithm that we're going to take advantage of soon. So I am going to choose to write down, I think I'm going to write down 2x plus 12y first equals 3600, and then I'll write down 30x plus 20y equals 30,000. And now I'm going to decide, well, how can I eliminate one of the variables? And I see here that if I add a multiple of the first equation to the second one, then I can have the 30x be canceled out by some multiple of 2x. Well, if I take the first equation and I multiply it by negative 15 and add it to the second equation, the reason I chose that is because negative 15 times 2 is negative 30. And if I add those together now, I can alter that second equation. So negative 15 times 2x is negative 30x, plus 30x is 0x. And negative 15 times 12, well, we can do that in our calculator if we want, comes out to negative 180. So if we take negative 180y and add it to 20y, we get negative 160y. And negative 15 times 3600 is negative 54,000 added to 30,000 is negative 24,000. Okay, so let me update our equations now. The first equation is still 2x plus 12y equals 3,600. Now we did multiply it by negative 15, but we only did that so that we could eliminate something in the second equation. So we're not actually changing the first equation, we're just using it as a pivot to help us clear x in the second equation. Okay, and that was productive in the sense that now we have a function that only involves y in the second equation. As a small operation, I'm going to keep track of what has been done here. We have taken negative 15 times equation 1, which we often write as row 1, and we'll see why we do this in just in a future video here. And we added it to row 2. And then I'm going to write a little arrow here to say that the only thing that changed was that when this was performed, negative 15 times row 1 was added to row 2, that we replaced row 2 with that result. Right? So here we see that row 2 is the only one that has changed, and that's what this notation stands for. It means we're only changing row 2. All right, well, in the second row, we could just divide both sides by negative 160. And that's precisely what we're going to do, but I'm going to write it in a slightly different way. I'm going to say instead of dividing both sides by negative 160, what we're going to do is we're going to take 1 over negative 160 and multiply it by row 2. And that's just going to create that change in row 2. Okay, so if I do that, if I only change row 2, I take 1 over negative 160, which is the same thing as dividing by negative 160. Then it doesn't change the coefficient of that first variable. It only changes the coefficient of the non-zero variables. And so 1 over negative 160 times negative 160 will give us 0x plus 1y equals, and then whatever negative 24,000 divided by negative 160 is, which comes out to 150. So we see we've solved for y. We know that from this equation, even though that we have this redundant term in here, 0x, that is going to become important because there is still a coefficient on x, it just happens to be 0. We know that y is equal to 150. So it might be tempting at this point to use substitution in the first equation and to solve for x by plugging in 150 for y right here in the 12y term. But let's keep things intact and just copy down our equations at this juncture after performing operation 1 and operation 2. So we have 2x plus 12y equals 3600, and 0x plus 1y is equal to 150. Let's continue to use elimination, but now because the second equation already has this coefficient eliminated, I can use the second equation, take a multiple of it, add it to the first equation to help me cancel out this coefficient of 12, make it a coefficient of 0. So what multiple of 1 do I need to take so that when I add it to 12, I get 0? Well, it's going to be negative 12. If I take negative 12 times row 2, and I add it to row 1, only changing row 1, then that will allow me to eliminate the y variable in the first equation. So negative 12 times 0 is not going to affect the addition here. Negative 12 times 0 is 0, plus 2 is still 2x. Negative 12 times 1 is negative 12, plus 12 is 0. And negative 12 times 150 is negative 1800, plus 3600 is positive 1800. So this now allows me to write my changed first equation, which is 2x plus 0y equals 1800, and 0x plus 1y equals 150. So in a sense, we did use substitution here, but we did it by performing it in an elimination approach. So we still kind of did substitution, we just didn't physically plug in y equals 150. And also one thing to note here is as we're doing this, notice that I'm not really so much concerned about saying negative 12 times 0x. You just heard me say negative 12 times 0 plus 2. Because as long as our variables are lined up in each column and our constants are over here on the right, then I don't really have to concern myself with the fact that this is 2x and this is 0x. As long as they are like terms, the same variables in each column, then adding the coefficients is completely mathematically legal. There's nothing wrong with that. And finally, in this last step, I see that I have 2x equals 1800, so all I have to really do is divide by 2. But of course, I'm not going to say divide by 2. I'm going to say let's take 1/2 of row 1. So that's implied division. And we're only going to change row 1. So we're going to take 1/2 of the first equation. Not going to change the second one in any way. 1/2 of 2 is 1. 1/2 of 0 is 0. 1/2 of 1800 is 900. And in my second equation, I haven't changed that, so I'm going to copy down my system one more time. My first equation is 1x plus 0y equals 900. My second equation is 0x plus 1y equals 150. And you can see we're done at this point, because the first equation says that x equals 900 and y equals 150 is my solution. We can write this as an ordered pair. We can say x comma y equals 900 comma 150. That's another valid way of writing it. Another way we'll often see this written as well is in a vector form, where we just sort of write that ordered pair as a column, and then in the second vector over here we just write down what the top component x is equal to and what the bottom component y is equal to. We can check our work. We can just verify that 900 quarts of beginner's juice and 150 quarts of advanced juice is correct, just by checking that in our first equation here, if we take 30 times 900 plus 20 times 150, we get 30,000 on the dot. In our second equation, we can check our work and say 2 times 900 plus 12 times 150, that gives us 3,600, which is exactly what we wanted. And now we know that we did not make a mistake anywhere in our work. And that completes the problem.